Oops. Good morning, everybody. Can you hear me?
Yes.
Thank you. Okay, so the other day we were dealing with, back up here. I think it was KA and KB. No, we were actually we were just about to get into buffers. That's how far we'd gotten. All right. So what I had gotten as far as doing was solving for the pH of a buffer solution without anything being added to it. And now we're going to look into what happens when we add either a strong acid or a strong base to the buffer and looking at the effect it has on the buffer. Now, I did give you a little bit of introduction to this, but this is what this slide here kind of really exemplifies exactly what's going on. So in the first part here, on each side, on both the right and left side, we start out with AH and A minus, and they're in equal amounts. When we add H plus, let me cancel that out here. When we add H plus, what happens is A minus reacts with H plus to form AH. And in the other case, so this is on the, I guess this will be on the left side. On the right side, it's AH plus OH minus gives A minus plus H2O. So those are the two different things that are happening here, with the H plus reacting with the A minus, the AH reacting with the OH minus. And you can see that in the case of adding the H plus, the AHs go up by 1 because we added 1 H plus, and the A minuses go down by 1. When we add OH minus to the same mix, the A minuses go up by 1 and the AHs go down by 1. Now, as long as there's enough A minus, or in this case AH, to react with whatever we're adding to it, then the buffer is still being effective. And the main point that's really important here is that when we add the H plus and the OH minus, it disappears. It gets eaten up by the buffer, as long as there's enough A minus and AH in the solutions in order to eat them up. They're gone. Once they're gone, they're gone. They turn into water, or they turn into AH, whatever happens here, but they disappear is the point. The H plus and the OH minus are gone. That's why the buffer is so effective. Now, there is going to be, in the case of the H plus, because we're forming a little bit more AH and now less A minus, the pH does go down a little bit. In the case of the OH minus, it goes up a little bit, but not very much. But if I was to add, say, 4 OH minuses or 5 OH minuses, then there would be a significant jump in the pH, a very, very significant jump, because then all the buffer has been eaten up. In the case of the H plus, if I added 5 of those, I'd see a very big drop in the pH. Does anybody have any questions so far? Okay, so let's look at the kind of problem that we're talking about here. 5.00 mils of 0.200 molar NaOH, that's a strong base, is added to this solution to give a total of 205.0 mils of solution. What's the new pH of the solution? So you'll notice that there's 100.0 mils of each buffer component initially. So we've got AH, we've got A minus, and we've got 100.0 mils of each. Now both of those get thrown into this mixture here, so we get the buffer made, and now that's going to be a total of 200.0 mils. And then in addition to that, now this is the next part, we're going to add 5.0 mils of 0.200 molar NaOH. Now this, of course, will lead to 205.0 mils of solution. That changes things as far as concentrations go, because we're now changing the volume of the solution. Because of that, everything now needs to be expressed in moles and not in molarity. And you'll see that as we go through the steps here in figuring out how to do part B, which is what happens when we add a little amount of strong base or strong acid. We're adding strong base in this case. So these are the steps to solving this problem here, is figuring out what the pH of this new solution is going to be once we've added the sodium hydroxide. So the first thing we do is we find the initial moles of acetic acid, or AH. We find the initial moles of A minus, and what we're talking about here is the initial moles in these solutions here and here, the ones I just put the check mark on. We're also going to find the initial moles of sodium hydroxide as well. So we're interested in the initial moles of each of these. I'll show you how we're going to do that in a second. The next thing we need to do is take into account what happens once we add the HCl or the NaOH. And what's going to happen is that for the NaOH, the AH is going to go down, and for the HCl, the AH is going to go up. If we add HCl for the A minus, it's going to end up going down, and for the NaOH, that's going to end up going up, the A minus. So what we're looking at in steps 4 and 5 are dependent on what we're actually adding. In this case, we're adding the NaOH. So the AH is going down, the A minus is going up. This is reflective of what's going on here on the right-hand side of this slide. When we add OH minus, because of what I had showed you here, you'll notice the AH goes down and the A minus goes up. If you can understand that, then you can see why, going back to here, the AH goes up, and down here the AH goes down, and in the other one the A minus goes up for the NaOH, and for the HCl the A minus goes down. Does anybody have any questions so far? Okay, I'll show you how we do this in a second. Then we have to convert these moles to concentrations, because we've got a new volume, and it's a total volume, which will be 205.0 mils in this case. And then we do what we need to do to find the concentration of H plus and get the pH of solution, just like we did in the previous step. All right, so let's look at how we do the math here. And it's best if it's just split into steps here. We'll start out with initial moles. And we'll start out with the AH. And the way we do this is to take the concentration, which was 0.100 moles per liter, and multiply it by the volume, and this volume is in liters. So that's 100.0 mils converted already into liters. And that comes out to be, in this case, 0.0100 moles. Now look at the significant figures here as well. We've got 3 sig figs, 4 sig figs, so the answer comes out to 3 sig figs. So that's the initial moles of AH. Now going back to the problem here, I'll show you where we get the numbers from. The buffer is made up of equal volumes, 100.0 mils of each, of 0.100 molar AH and 0.105 molar A minus. Anybody got any questions? Okay, so for A minus, we've got 0.105 moles per litre times, again, 0.1000 litres. That would be 0.0105 moles for A minus. Anybody got any questions? So this is initial. Now we have to find the moles of OH minus we're actually adding, and that's going to be 0.200 moles per litre, and that's times 0.0050 litres. Just make sure I've got the right number of zeros there. No, it's 5.00. So there's one more zero here. And that comes out to be, I think, let's see, well, I won't think about it, I'll just do it from here, 0.00100 moles. Again, 3 significant figures. Remember, leading zeros aren't significant. All right, does anybody have any questions? So those are all the initial moles. The next thing we need to do is figure out the reaction moles, or what happens after the OH minus reacts with the AH in this case here, and what happens to the AH and what happens to the A minus. So for the case of the AH, what happens is that the moles is going to be 0.0, well, let me write this out, moles of AH initial plus, minus moles of OH minus. So what's going to happen is we know that the AH is going to go down because the AH is reacting with the OH minus. Now that would be, looking at what we have up here, 0.0100 moles minus 0.00100 moles, which comes out to be 0.0090 moles. So again, looking at the significant figures here, we've got 4 decimal places, 5 decimal places. The answer comes out to 4 decimal places. We do the same thing for A minus now, but it'll be the moles of A minus plus the moles of OH minus, which is 0.0105 moles plus the moles of OH minus, which is 0.00100 moles, which would be 0.0115 moles. All right, does anybody have any questions? The main thing I want you to understand is why it's minus here and plus here, where I've circled. That's really the key. If you can get that, then you're good. Does anybody have any questions?
In finding the initial moles for the OH minus, can you explain where you're getting the 0.005 from?
Okay, so if you look at the question, Jiz, it says we're adding 5.00 mils of 0.200 molar solution. So the 0.00500 is the 5.00 converted into liters.
Okay, thank you.
All right, any other questions? Okay, again, the plus and the minus are the result of what's happening in the reaction mixture when we add OH minus. The AH goes down, excuse me, because it's reacting with the OH minus, and the A minus goes up. So again, I will just put that over here just so that you can be super certain of what's going on here. This is the reaction that's occurring. So you can see that the AH is going to go down when it reacts with the OH minus. The A minus is going up, and that's why it's minus on the AH and plus on the A minus. Does anybody have any questions? Okay, so the next step, once we've got the moles, is to convert them back into concentrations. So the concentration of AH now will be the moles of AH divided by the total volume. In liters, which would be 0.0090 moles divided by 0.2050 liters. Now that's the total volume. So that's 100.0 mils of each buffer plus the 5.00 mils of sodium hydroxide that we added. Anybody have any questions about this? Okay, so the amount there is going to be 0.0044 moles. And you see that's going to be two significant figures because the 0.0090 moles is two significant figures. That shouldn't be moles, it should be molarity. There we go, moles per liter. The A minus is going to be moles of A minus divided by, again, the total volume in liters, which is going to be 0.0115 moles over 0.2050 liters, which comes out to be 0.0561 molar. That's going to be three significant figures. Does anybody have any questions? And the last step, we want to find the concentration of H plus and then figure out the pH of the solution. So what we're using here is the equilibrium process. AH gives A minus plus H plus. We have the initial concentrations and we're looking for the equilibrium concentrations, especially the equilibrium concentration of the H plus. Now the initials are going to be what we just calculated here. For the AH, it's 0.044. For the A minus, 0.0561 molar. And the H plus here is 0. Now the H plus here is only the result of what happens when the AH is turning into A minus and H plus. At equilibrium, the AH is breaking down a little bit into A minus and H plus. And that means that the A minus goes up and the H plus goes up. Now, this is really simple to explain here. Now, after we've added the OH minus, what we've got is a mixture of AH and A minus in the solution. The OH minus is completely gone. It's been reacted. So any AH that's in the solution, some of it now is going to break apart. So I've already got A minus in the solution, and some of the AH will break apart into A minus and H plus. So this AH here is breaking apart into A minus and H plus. So you can see that the AH is going to go down by a certain amount. The A minus is going to go up by the same amount. The H plus is going to go up by the same amount. Now these signs here, they don't change even if we're adding sodium hydroxide at the beginning or H plus at the beginning. That doesn't affect what's happening here because that reaction has already occurred back over here. Either the AH has reacted with the OH minus or the A minus has reacted with the H plus. That doesn't matter. That's not the same H plus as we're seeing over here. This is happening after this reaction has occurred. Does anybody have any questions? Okay. Because it's a buffer, and we're told that at the very beginning of the problem, we can say it's a weak acid because that is the definition of a buffer. Which means that we can assume, and we don't even have to validate this, but we can assume that 0.044 minus E is going to approximate out to 0.044, and 0.0561 plus Z is going to approximate out to 0.0561. So we don't even have to validate that. We can make the assumption because the buffer is consisting of a weak acid and it's conjugate based by definition. Anybody have any questions so far? Okay, so once we've got those, then we can use our Ka expression, which is based on this reaction that we have here. It's going to be A minus times H plus over AH. The Ka was given in the problem 1.80 times 10 to the negative 5. A minus we've already got as 0.0561 times the concentration of H plus and 0.044 as being the concentration of AH. Then we can solve for H plus, which in this case I think, let's have a look at 1.4 times 10 to the negative 5. Is anybody uncertain about how to do that conversion? Anybody have any questions about that? In your calculator, it'd be 1.80 times 10 to the negative 5 times 0.044 and then divided by 0.0561, and that should give you your answer. The next thing you would need to do is find the pH. The pH will be the negative log of the hydrogen ion concentration. And that's going to be 4.85. And this has two significant figures, which translates to 2 decimal places at the end. So that's why we get 4.85 when we finish the math on that. So what we noticed here was that in the beginning, when we did part A, we came up with a pH of 4.767. And then after we added the OH minus, it went up to 4.85. So it didn't go up by much, but it did go up a little bit. And that's what we expected when we did the OH minus. Does anybody have any questions? Anybody have any questions?
I have a quick question.
Yes, Kate.
In the table, why does it have 0.100 divided by 2?
So
Like,
this
why
is
are they...
okay. So this was when we were doing the buffer, and what happened was it was made up of equal volumes of 100.0 mils of each of these. And what that means is when you have 100.0 mils of each and you add them together, you get 200.0 mils, which dilutes each concentration by half. So that's where the divided by 2 comes into play in that first part.
Okay.
Now you don't have to do that here with the other steps because we're actually converting into moles. So we don't have to worry about doing that here. We're already doing the other work to get that sorted out. All right, does anybody have any other questions? All right, let me show you, let's go back to this. Let me show you some of the resources we have in a buffers folder. I've got a buffer problems document here in the buffer folder. And I've got lots of examples of what's going on here. Some of them with the addition of sodium hydroxide. So example 1 was the one we just did. That started out at 4.767 and went down to 4.85. I'm going to show you this second example here, where we start out with acetic acid and the acetate ion, 0.150 and 0.140. In this case, we're adding 10.0 mils of 0.150 molar HCl. So we're adding H plus to the solution. And you can see what happens is that initially the buffer is 4.715 and it goes down to 4.655. That's because we're adding H plus here. So let's look at, this is the one we just did. Let's look at, here we go. So this is the one that's got the H plus being added. So initially we figure out the moles of AH, which is what we just did previously as well. We get the moles of AH, which is going to be the concentration times the volume that we're using. In this case, it's 150.0 mils. In the case of A minus, again, it's 150.0 mils that we're starting out with initially. And then with the moles of HCl, which is going to end up being the moles of H plus here, it'll be 0.150 moles per liter. That was the molarity multiplied by 10 mils converted into liters. So we're doing the same kinds of steps here for this one as we did previously. The difference now is when in the reaction step. So I want you to contrast this, and I'm going to find the thing here. There it is. I want you to look at the reaction moles on the screen here on the right side and compare it to the reaction moles over here. Do you see how in this instance it was minus and plus for the AH and the A minus, and here for the AH it's now plus, and for the A minus it's now minus. So these get flipped around. That's the only change that occurs here. The reason for that and I'm going to shrink this screen a little bit. The reason for that is in this instance, you can see the reaction at play is AH plus OH minus gives A minus plus H2O. For this one, it's A minus plus H plus gives AH. Or if you wanted to, A minus plus H3O plus gives AH plus H2O. Either way, it's the same thing. But the point is, you can see that the A minus is going to go down, which is why it's minus here. But the AH is going to go up. That's why it's plus here. It's the opposite of what happened when we added the sodium hydroxide to the buffer solution. Does anybody have any questions? Because that's really the most important part. All right, so once you've got the moles, then you can divide by the total volume, which in this case was 310.0 mils converted into liters. And we do the same steps as we did previously and making that assumption and then solving for H plus, and that's how we get the pH at the end. But I think it's good going into these problems to know whether or not you're expecting it to go down a little bit or up a little bit. And if it doesn't do what you expect it to do, it's probably because you've made a mistake. And if you've made a mistake, it's most likely at this step here where you're doing the reaction, finding the reaction moles here or here, depending upon what you're adding, whether you're adding H plus or OH minus. Because if you mix these up, you are going to get the opposite result to what you expect. Does anybody have any questions? Okay, let's go take a look at the kinds of questions you're going to see on the test here. Yeah, I tell you, what happens here is that this is why some people don't do very well with test 2, is because, well, and I'm like a broken record, I know, but people leave things to the last minute. It's unbelievable, isn't it? Did you realize that? Actually, people leave things to the last minute. And there's just too much to figure out in too short a time. So it's triage, and what happens is corners get cut, and things just don't get understood. And it's just it's just a very sad situation. Is what it ends up being, and it doesn't have to be that way. But I don't know. I can't make people start doing stuff early. And what annoys me is I get the blame then. Oh, it's too hard, Dr. Musgrave. There's too much material. Yeah. All right. That's end of rant. Okay. Let's look at the kinds of questions you're going to see here. Now remember, there's also videos for each of these kinds of questions. So if you're uncertain of the wording or what's being looked for, then you can look at those videos as well. Okay. So let's look at question 16. A buffer is made up of equal volumes, and it gives you the volumes here, of AH and A minus. And then it tells you that a certain amount of sodium hydroxide is added to the buffer. How many moles of AH are present after the addition of NaOH? Okay, it says please use correct significant figures as well. And because it said that, you should do it. So buffer is made up of equal volumes, 698.0 mils. So we need to find the initial moles first. We'll start out with the AH, and then we'll do the A minus, and we'll do the OH minus here as well. So for the AH, it is going to be 0.742 moles per liter times 0.698 liters. 0.6980 liters, I should say, which comes out to be, well, let's do the math on it. 0.5179 or 0.518 moles. Then we do the same thing for the A minus. Now, if you're looking at what the question's asking for, it's actually just asking for how many moles of AH are present. So we don't even really need to do the A minus at all. We do need to figure out the OH minus though, and that's going to be 0.226 moles per litre times the volume in litres, which is 0.01537 litres. And that's 0.00347. Now, because we're looking at AH, it's going to be AH plus OH minus gives A minus. So we're expecting the AH will go down and the A minus will end up going up. Now, what we're looking for though is the AH. So the result would be, and this will be the final or reaction moles of AH. Reaction moles of AH will be initial moles of AH minus the initial moles of OH minus. Which is going to be 0.518 moles minus 0.00347. Now, when we take significant figures into account, this is going to end up being 0.515 moles for the AH. Does anybody have any questions? Anybody have any questions? Okay, in question 17, it's a similar question, but this time now HCl is being added to the buffer, and we're looking for the moles of A minus that are present. So we're going to do a similar process here. We'll look at the initial. The initial moles, and we'll do we're only interested in the A minus, so let's look at the moles of A minus. Which is going to equal 0.854 times the volume, which is 238.5, which is converted into litres, 0.2385 litres. Which comes out to be 0.204 moles. And then we need the moles of H plus being added here, and that's going to be 0.546 moles per litre times the volume 0.00854 liters. And that's 0.0466. 0.00466 moles of the H plus. Now, when we're looking at this reaction, it's A minus plus H plus gives AH. So we're expecting the A minus will go down and the AH will go up. So that means that the reaction moles of A minus now will be the initial moles of A minus minus the initial moles of H plus. So that's going to be 0.204 moles minus 0.00466 moles, which I think ends up being 0.199 moles once we take significant figures into account. Does anybody have any questions? So the main point of question 16 and 17 is knowing if you have to add or subtract. You know you have to find the initial moles of something. What do you find the initial moles of? Well, whatever you're being asked for. In this case, it's A minus for 17. For 16, it was AH. Then you have to figure out what's happening when you add H plus and you add OH minus, and it's either going to go up or down, and you need to be able to figure that out based upon which reaction is occurring, and then you can figure out the moles at the end. Does anybody have any questions? I can't believe nobody has any questions about this. All right, I'm going to do a quick poll here. Actually, I think I might have this poll somewhere else. Let me see if I've got it. I don't want to do that. Edit. I think it might be. Here we go. Yeah, that's it. That's the one I want. Yeah, poll 2. Okay. Okay. I'd like you to answer this question here, please. See where I'm at. Don't worry about the I was not here Tuesday. I'm really only interested in the first 3 topics. Okay. All right. Almost everybody's voted here. So the situation I'm seeing here is it's about 1/3 to, well, yeah, a little bit over half to. That's kind of what I've been seeing as we go through this anyway, with all the other topics as well. What it means is that the people who aren't understanding need to get some help from me, or they need to get some help from a tutor, but they definitely need to get in and start studying these test questions and figuring out what's going on. I mean, but the thing is that if you wait until the last minute, and that's what people tend to do, then it ends up not being enough time to understand what needs to be understood. It becomes you know what happens. Okay. Does anybody have any questions? Okay. Okay, so 16, 17, now 18. you'll have to figure this one out yourself and figure out which table you're going to see. The clue I'm going to give you here is that it doesn't matter whether a small portion of NaOH or H plus is being added. The answer is going to be the same table for number 18, regardless of what the situation is. And that's because this table is after the reaction has occurred. So it's after this point that we're doing in questions 16 and 17. So after this, it doesn't matter. I mean, whether it's HCl or NaOH, it's the same table. I'll ask you to figure that out yourselves. The last question here is what's the pH of the buffer after the addition of 0.229 molar NaOH, and that means going through and doing the entire thing that we just did, the entire procedure that I just showed you on the PowerPoint slide in order to get to the answer here. So you'll do that for number 19. Does anybody have any questions?
Just to clarify, when you said we have to figure if it's subtraction or addition, that's for the part where we're finding the reaction mole, right?
That's right.
Okay.
And when you're adding H plus, A minus goes down and AH goes up. When you're adding OH minus, A minus goes up and AH goes down. That's the main thing I'm trying to get you to see here, with the reasoning being set out by this picture. Not just this picture though, also the reactions. And I think if you just have this in your mind, I mean, put very simply, this is what's going on. All right, that's the main thing. So when it's a down arrow, it's minus. When it's an up arrow, it's plus. Is that okay?
Yeah, thank you.
All right. Does anybody have any other questions? Okay. So for those of you who are having trouble understanding it, make sure that you start studying these problems, these very problems that I just went through on the ungraded copy. If you're still having trouble with it, then you have to seek either help from me or somebody on tutor.com, which can be an SBC tutor, by the way, or me, either one. But you need to seek help, and you can't leave it till the last minute. All right, any other questions? Let's take a look at something else here. So this is the buffer practice quiz problem. And what we're going to be doing first of all is determining the initial pH of the buffer. And we'll do that by using our equation for the actual dissociation of the weak acid. So the initial molarity is what we're dealing with first. Here we go. That's going to be 0.185 over 2 and 0.186 over 2, and then 0 on the H plus. At equilibrium, it'll be 0.185 over 2 minus Z, and then 0.186 over 2, plus Z, and then Z for the H plus. Now, assuming it's a weak acid, and we can do that because it is a buffer, then we're going to get 0.185 over 2 minus Z is going to approximate out to 0.185, and the 0.186 over 2 plus Z is going to approximate out to 0.186. So then we can use our Ka expression, which is going to be A minus times H plus over AH. The Ka is 4.68 times 10 to the negative 5, and that's from the problem. And then we can substitute in these values. That should be over 2, and that should be over 2 as well. Sorry about that. So the A minus there is 0.186 over 2 times concentration of H plus, and that's over 0.185 over 2. Then we can solve for the concentration of H plus, and when I'm doing that, I'm just going to ignore the over 2's because those cancel out effectively, and we're going to have 4.68 times 10 to the negative 5 times 0.185 divided by 0.186, and that's going to be 4.65 times 10 to the negative 5 for the concentration of H plus. And we take the pH, that'll be the final amount here. pH is going to equal, if I take the log of that, 4.332 is what I get for the initial pH of the buffer. So that's the first part. The next thing I need to do is figure out what the I'll just open up another window of this here, and this will be the final pH after we've added the 0.199 molar NaOH. So this is the final pH here. The first thing we need to do is figure out the initial volume, and that's going to be, well, we're given the total volume is 228.6. We subtract out the amount of 17.1 mils for the sodium hydroxide and divide that by 2. The reason is because it's made from equal volumes. So when we do the math on that, we have 228.6 minus 17.1. Divide that by 2, and that's going to be 105.8 mils, and that's for the initial volumes of each of those. So now we're going to find the initial moles of each. We'll do the AH first, and that's going to be 0.185 and that's moles per liter times 0.1058 liters, which is the volume here we have in liters, And what we get there is 0.0195, 0.0196 moles. Now for the A minus, it's going to be 0.186 moles per litre from the problem here, 0.186 times 0.1058 litres, and that's 0.0197 moles. Now we need to find the moles of OH minus added as well, and that's going to be 0.199 moles per litre times 0.0171 litres, which comes out to be 0.2161 or 0.216. Something's up with that. Let's try that again. I don't think that's right. 0.199 times 0.0171. No, that's better. That's 0.00340 moles. That seems right. Okay. Now, since we're adding OH minus, then according to our equation here, AH plus OH minus gives A minus plus H2O. I'm expecting the AH will go down and the A minus will go up. So we'll get the moles of, I'll do that here, we'll do the reaction moles. So for the AH, it's going to be moles of AH initial minus the moles of OH minus initial, which is going to be, in this case, 0.0196 moles minus 0.00340 moles, which equals clear that out. It's 0.0196, by the way. So 0.0196 minus 0.0034, which is 0.0162 moles. And then we've got we need to find the moles of A minus. I'll start that in another window here. And that's going to be the moles of A minus initial plus the moles of OH minus initial, which is going to be 0.0197 moles plus 0.00340 moles. And that's 0.0231. So next we find the concentrations using the total volume. So we need the concentration of A minus and concentration of AH. So for the concentration of AH, it's going to equal the moles of AH minus the volume in litres. Let's make it total volume. Now we do have the AH here, it's 0.0162 and that's over the total, which is 228.6, but in litres, 0.2286 litres. So that'd be 0.0709. That's molarity. And for the concentration of A minus, it'll be moles of A minus divided by the total in litres, which is going to be 0.0231 moles divided by 0.2286 litres. Which comes out to be 0.101 molar. So those are the final concentrations there. Now we can solve for the pH. Well, let's do the H plus and then we'll get the pH from there. And this will be the final pH. And again, we're using our AH gives A minus plus H plus. We have our initial. We have the equilibrium. Now the initial is going to be what we calculated, 0.0709. And the initial on the A minus is 0.101 and the initial on the H plus is 0. Then at equilibrium we lose some of the AH, we gain a bit of A minus, and we gain Z here, which is the H plus. And because it's a weak acid, we can assume that it's 0.0709 minus Z is approximately 0.0709, and that 0.101 plus Z is approximately 0.101. Then we get the Ka, which is going to equal the A minus times the H plus. over the AH. The Ka is 4.68 times 10 to the negative 5. The A minus 0.101. The H plus is what we're solving for, and that's over 0.0709. And then the concentration of H plus then, 4.68 times 10 to the negative 5 times 0.0709 divided by 0.101, and then that'll be 3.2 times 10 to the negative 5, 3.29 times 10 to the negative 5. The pH then is going to be the negative log of that, 4.48, 4.483. If we take significant figures properly into account there, 3 sig figs means 3 decimal places on the log, 4.483. So that's the final pH. Let's compare them. So the initial pH, oops, and then the final pH. I think the initial was 4.332 if I remember rightly. And the final here is 4.483. Which there is a difference there of about 0.15, and that would be the answer you'd look for. And yeah, there is a 0.15 here. Now since it's an increase, the answer would be plus 0.15, so that would be that's what you should go for in the answer there for that one.